I'm the one speaking today, but this is joint work with Chris Kanich, who's another faculty member in the department, Shubham Singh, our wonderful graduate student who just defended, and one of our fantastic undergraduates, Bhuvni Shah, who started with us after her freshman year through the college's guaranteed internship program and continued onwards seeing the project through. And so we've seen kind of in a lot of the presentations today, right, AI popping up in one way or another, right? And so rightly so, there's a lot of focus on how can we ensure that AI behaves in societally useful ways when we want to do it. And so computer scientists have been thinking about this for a while, starting with kind of very simple problems like classification. What does it mean to be fair when we are sort of trying to get an algorithm that can apply labels to things? And kind of what can go wrong? Well, you know, like the demonstration that Dale gave us earlier, the puzzle he gave us was not really magic, it was math, and that's the same thing with AI, right? And what are AI systems doing? We create some formula and create a bunch of code that says, make this number as big as possible, right? And it knows nothing else. So it'll just go and the code will go and make that number as big as possible, disregarding anything else we might care about that we forgot to tell it about, right? And so there's been lots of work. How do we bring these other considerations into tasks like classification? But of course, most of the things we care about in the world are not necessarily classification, right? So if you want to use AI in some societally important tasks, say, some of the decisions made and how resources are allocated in the city of Chicago. So we went looking at what was available to kind of look at these systems in Chicago's civic data. And it turns out there's quite a bit and been work done already about could you use lots of this data to improve the way food inspections are organized, to try to target inspections at the places they're most likely to find problems and better improve public health. And some previous work had kind of shown that the answer was yes. And we kind of went back and looked at like, how are those gains distributed? Are those gains being distributed in some sort of equitable way if you just turn the system loose and say, do this as well as possible, don't worry about anything else? And it turns out they're not. So I won't go into the metric, but the blue bars are kind of various notions of how fair things look with the default model, and you'll see they're all around 0, which means basically everywhere in Chicago, all these different neighborhoods are getting about the same amount of benefit from the system. They're all right around the average. If you just naively train an algorithm and set it loose, you get the orange bars, which you see are very much not 0, right? There are some neighborhoods that are getting a lot more benefit from others from this algorithm. What's going on? It turns out that different inspectors have different policies. So if you just take the data, there are some sanitarians you send them out, 40% of the time they find a serious problem. Others, 2%. And this has to do with the way they're trained, different approaches to try to achieve justice, because they want public health, but there's different ways of doing it. You kind of smack people with a stick. And so if you don't kind of correct for these biases, the algorithm will learn from the data, and where those sanitarians are not random. It'll choose where to send inspectors based on kind of these past patterns in the data. And so it's important to take into account all of these factors in the way the AI system is going to be used. We've done kind of lots more work in this vein since that I'm happy to talk about, but I will stop standing between you and the end of these presentations.